Phases of Matter, Lecture B. Today we are going to start by talking about gases. Gases are going to get 2 days worth of lecture because of the nature of gases, because they are far apart and they have lots of space in between. When we change the conditions of the environment that a gas is in, we can change the behavior of the gases. Solids and liquids are much closer together, and so changes in temperature and pressure won't affect their volume and their temperature and their pressure as much, so we will spend less time talking about them. Gas particles are far apart, randomly arranged, straight line motion. These little fancy lines off of the edges of these gases are supposed to imply motion. So they're going to move in a straight line until they hit something. They're either going to hit the side of the container and bounce off, or they're going to hit each other and then bounce off of each other and move in an opposite direction. And they will bounce around and take the size and shape of the container they're in. So we say they have an indefinite size and an indefinite shape. Sometimes instead of size, they'll say volume. You might have heard that stated as they take the size and shape of their container. It's another way of saying the same thing. Down here, I want you to notice something that says STP. STP is a very common abbreviation. It means standard temperature and pressure. If you look at reference table A, so find your reference tables. Very front page, very first table, reference table A, is standard temperature and pressure. So here are your values for STP. Usually when we do lab work at a room temperature, and a lot of times they say room temperature is about 298 Ks. That's warmer than our lab room, but much warmer than standard temperature. Take a look at standard temperature. Standard temperature is at 0 degrees Celsius, or 273 Kelvin. Standard pressure is just room pressure. That should be pressure at sea level if there's no big weather system running through. That's usually okay for lab. Our lab work is usually done in a temperature warmer than what standard pressure is, or standard temperature is for gases. So our data doesn't always work out the same. There's going to be a lot of reasons why our lab work with gases doesn't work out ideally. And so we're going to start by talking about what an ideal gas is and why real gases don't act like ideal gases. So this kinetic theory, or the ideal gas model, says that the perfect gas would behave like this. So it says that they're in constant random straight line motion, that all of the energy transferred between colliding particles is perfect. That means the collisions are elastic. That's a fancy way for saying if they hit with 100 newtons of force, when they bounce off, they still have 100 newtons of force. That would mean no friction, no heat. Ideal gases would also have no volume. So that means they wouldn't take up any space. Now, we already said matter is anything that has mass and takes up space, and that gases are matter. So this would mean that gases would not be matter. Negligible, so small that it doesn't make a difference. But if you take a balloon and you fill it up with helium, and helium is a pretty small gas, it will fill up the space inside of the balloon and push the balloon out. So we know that gases really do have volume. And the last key part is that gas particles have no attraction for each other. So if we put two gas particles together, they're not going to stick together. Gases have very low attraction for each other, but because we can turn them into solids and liquids under the right conditions, we know that they have some attraction for each other. So it's not as much as solids or liquids, but they definitely have some attraction for each other. So an ideal gas: perfect straight line motion, perfect transfer of energy, negligible volume, no attraction for each other. Okay, now real gases. Real gases will not fit this assumption. Some behave better than others, but not all of them. So real gases don't fit because real gases are attracted, have some attraction for each other and their environment. And this means when they're moving, something might attract them even just a little bit, and that means that their paths are not always straight. Their paths will sometimes curve towards what they're attracted to, so they don't meet the first one. There is this thing called friction, which tends to produce heat, and so when the gas particles collide with each other, some of their energy is lost as heat to friction. It gets transferred to the container that they're in. We know that they have some volume because we can fill up a balloon with them. And you can only put so much gas into a container or cylinder. If you try to put too much gas in, most of you know that the container is going to explode, so you have to be careful of that. So they do have some volume, and we already said they have some attraction for each other. So these are ways that they deviate. Now we can get gases to behave more ideally, and these two right here, they like to ask a lot. What are the conditions? What are the conditions to get a real gas to act most ideally or least ideally? So if we want a gas to act most ideally, we want the particles far away from each other and moving fast. Because if they're farther away and moving faster, there's less attraction, the collisions are more elastic, and there's more space in between the particles, so that means the individual particle's volume compared to the space they're taking up is lower, so we get closer to this negligible volume. Conditions for making things behave most ideally then are going to be high temperatures. That's going to let them move very, very fast, and low pressures. That's going to let them spread farther away from each other, which will reduce the amount of attraction and increase the amount of space that they're taking up, which will make the volume of the gas particles themselves less important. Sometimes they want to know when particles are going to act least ideally. So if those are the conditions for most ideal, for least ideal, we want the opposite. We want them close together, and we want them moving slower. Closer together is going to let them clump up, be more attracted to each other. If they're moving slower, they're going to compress down. They'll be attracted to each other. They'll bump into each other more, and the gas particles themselves will start to account for more of the volume that the gas is taking up. So how do you get them to slow down and get closer together? Well, it's pretty simple. We just do the opposite that we did with the most ideal. So instead of high temperatures, you want low temperatures. And instead of low pressures, you want high pressures, and that will push the particles closer together. Here is another important point. The bigger and heavier a gas is, the less ideally it will act. So as far as mass goes, you want heavier particles will act less ideal, and lighter gases will act more ideally. And so our two smallest gases, the ones that have the lowest mass and the smallest volume, are going to be hydrogen gas that has a mass of 2, and we call them AMUs, atomic mass units, or helium, which has a mass of 4 AMUs. So those are the really tiny guys. The next smallest gas would be nitrogen, and it has a mass of 28. So hydrogen and helium, definitely the little tiny small gases. Those are the ones that are going to behave most ideally. Because this is chemistry, and we like to take quantitative observations and analysis whenever we can, we do have a mathematical relationship when it comes to gases, and it's something that we call the combined gas law. So in real life, pressure and volume and temperature are all going to be related to each other. It's very hard to set conditions where you change only one or two of those things and not all three. So we have this mathematical equation called the combined gas law. If it's a mathematical equation, which table should we look at? Reference table T. So there it is. PV over T equals PV over T. The subscripts here, these 1s and 2s, the little subscripts, 1s and 2s, those are just referring to your samples. So think of the 1s as meaning the original sample and the 2s as being the ending sample. And it doesn't really matter which side they go on as long as you group all of the conditions for what the gas was at one point in time together on one side of the equation and all of the conditions that the gas was at another point in time on the other side. What I really like about the combined gas law in this equation is that we can use it for all of our chemistry work when it comes to the gas laws and the calculations, because sometimes they're going to artificially make one of the conditions stay constant. So they'll say it's at constant pressure. And what you can just do is ignore whatever remains constant. So if they tell you the pressure is constant, you're going to take that combined gas law and ignore the pressure. So you're just going to take pressure out and have V1 over T1 equals V2 over T2. If they tell you the temperature stays constant, then you're just going to ignore temperature. And you have P1 V1 equals P2 V2. And then, of course, last but not least, if the volume stays constant, so you have some kind of rigid container and the volume can't change at all, you have P1 over T1 equals P2 over T2. So you can just ignore what stays constant. If all three things change, you use the equation exactly the way it is. One of the mathematical things that I want you to look at right now, though, is look at how these equations work out. If the volume staying constant and we have pressure and temperature, what type of relationship is that? Well, if I have 10 over 10, which equals 1, and I change the temperature to 100, what would the pressure have to be? Well, the pressure would also have to go to 100 so that it stayed 1. So if I increase one variable, I must increase the other. Because of the way that this equation is set up, I know that this is a direct relationship, which means volume and temperature must also have a direct relationship. If I increase one, I increase the other. Down here where we have the equation with pressure and volume, if I were to change one, so if I had, say, 10 times 10, and I increase 1 to 100, the other one is going to have to be what? Well, 100 equals 100x. This one's going to have to go to 1 in order for this to stay balanced, which means when I increased one, I had to decrease the other. That means that pressure and volume have an inverse relationship. When you see a question, again, I want you to look for the key parts. A 50 milliliter sample of a gas is at 500 K and has a pressure of 60 atmosphere. So we're starting with, if the temperature is changed to 250 Ks and the pressure is changed to 20 atmosphere, what is the new volume? So when we end, so we just plug those into our equations. PV over T equals PV over T. So we're going to have a pressure of 60 and a volume of 50 over a temperature of 500. And that's going to be equal to a pressure of 20 times, I don't know what the new volume is, over a temperature of 250. One of the things I want to point out to you right now is these temperatures must be in Kelvin. Temperatures for these must be in Kelvin. And sometimes they'll make the question extra hard by giving you one temperature in Celsius and one in Kelvin, so you have to make sure you change your Celsius into kelvins. So 6 is 20x over 250. We're going to multiply both sides by 250, 1500 equals 20x. And then, of course, to solve for x, we're just going to divide by 20. And our units then for the volume will be the same units that we started with. So if they start with liters, you're going to end with liters. They're starting with milliliters, so it will be 75 milliliters. The combinations of just two conditions at a time, so combined gas law, all three changing, the combinations of two at a time all have specific names. So pressure and temperature is called the Gay-Lussac law. Volume and temperature is called Charles's law. And pressure and volume is called Boyle's law.